Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on amplifier. Okay, so for this video, I'm going to share how can we actually determine our amplifier design or our transistor design, they will be stable using Rollett Stability Factor K. So basically, this will be the objective of this video. Okay, how to make use of Rollett Stability Factor to determine whether our amplifier design, our transistor design, they will be stable or not. This will be the part 14 series discussion on amplifier. So guys, if you're keen to know more about amplifier, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on amplifier. This is my email. If you have any question regards on this discussion, please drop me an email. Or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. Before I continue, I'd like to urge you guys to help this channel by pressing the like button. When more you guys actually help to press the like button, this video will have a better chances to reach up to a larger audience. So guys, help me press the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Let's quickly understand what is actually a Rollett Stability Factor. So basically this K term, which represent Rollett Stability Factor, in fact, is a very important parameters that we use to analyze the stability of a two-port network, such as amplifier or transistor, especially in high frequency, like radio frequency or microwave frequency. So this Rollett Stability Factor, in fact, is named after this inventor, John Rollett, who firstly introduced this. Let's take a look. What is this equation? So basically this is an equation for Rollett Stability Factor. I will have another video, part 15 series discussion to show you an example how can we actually compute this Rollett Stability Factor. But at this moment, let's take this equation. So I just want to highlight a few things. So basically you see that this is actually what we call the magnitude. We forget about the imaginary number. We only focus on the magnitude. So you see this delta here. So how to get this delta is in fact from this equation here. So this equation, you still need to consider the imaginary number. Firstly, what you need to do is you need to multiply S11 with S22. Then you need to multiply S12 with S21. Then you use this equation minus this equation. Then we have this so-called delta number, which we need to sub into this equation. When we actually sub into this equation, remember, we only just need the magnitude number. So after that, we compute the K value. So basically the K value, there will be two range. One is the K will be more than 1. Another range is K will be less than 1 or equal to 1. So basically this will be so-called classified into two different classes. So when K is equals more than 1, so when K is more than 1, this is what we call the unconditionally stable, which means that the amplifier or the transistor that we actually design, they will be always stable as long as we ensure that the load and the source impedance, they need to be passive. Not active, but just passive. With this, basically the design will be always stable, because they will not oscillate. So basically under another so-called extreme case, which means that K is less than 1 or maybe equals to 1. This is what we call the potentially unstable, which means that there is always a percentage that the amplifier or the transistor that we actually design, they will be unstable. So therefore we need to so-called state up the condition so as to ensure the amplifier that we actually design or the transistor that we actually design, they will be still remain stable. So we need to specify the condition. But for this case here, when K, which is let's say equals to 1 or less than 1, as I mentioned earlier on, this is what we classify under this potentially unstable, which means that the design, they can be potentially unstable, under certain load or source impedance condition. Okay, so why we need to study this Rollett stability factor? Okay, in fact, this is very crucial when we actually design amplifier. When we actually design amplifier, we need to ensure that the circuit does not oscillate. Why? Because once they oscillate, okay, so basically we may have potential performance degradation or even the damage to the amplifier design. So basically, this Rollett stability factor, okay, for example, we need to ensure that it's more than one, okay, so as to ensure that they does not oscillate, which means that we are actually protected from any potential damage to the circuit design. Okay, so it is also often used alongside another stability measure, which is known as the MU factor, so as to fully characterize the stability. Coming to the practical use, okay, we as an engineer, we always use this K so as to evaluate the stability of the transistor or amplifier during the design process. Okay, if you still remember when K is less than 1 or equals to 1, this is what we call the potentially unstable. Okay, so once under this kind of situation, we need to have addition stabilization techniques. Okay, for example, we can add some resistor, or in fact, we can have some form of feedback network so as to ensure that the amplifier or the transistor that we design, okay, they will be still remain in the stable so-called operation. Okay, so basically this is what I mean here. So once we have this kind of situation, K less than 1, then we may have so-called offer another addition stabilization technique. Either we add the resistor or some form of feedback network so as to ensure the transistor or the amplifier that we design to remain under stable condition. So basically, this is what it means over here. So in summary, the Rollett stability factor K, in fact, is a fundamental metric to determine, okay, whether the RF or microwave circuit that we actually design are able to remain stable. Next, okay, another factor that I mentioned earlier on, which is the MU factor. Okay, so basically this MU factor of stability of an amplifier, again, is also another parameters that we need to use to assess the stability of an amplifier circuit, okay, especially in high frequency application. Okay, so this MU factor actually quantified, okay, the worst case effect of uncertainty on the stability of a control system. Okay, so anything out of this, okay, so basically this is basically the worst situation. So as long as you are over this, then your amplifier design will be definitely unstable. Okay, so basically this is what you want to say. Okay, so the MU factor actually help to determine, okay, whether an amplifier, whether they will oscillate or they will remain stable under specific operating condition. Okay, again, this is another set of equation. Okay, so this video I'm not planning to discuss the equation, but rather than that, okay, let's quickly understand, okay, under again two extreme case, when this MU factor is more than 1, okay, or MU factor less than 1. Again, when MU factor is more than 1, same for the so-called Rollett stability point here. So basically, once they are actually more than 1, then the amplifier or the transistor that we actually design, they will be under this unconditioned stable, which means that 100% they will be stable if we have passive load and also so-called passive load and also the passive source impedance. So this is to ensure that the amplifier that we design, they will be 100% stable. Again, okay, under this kind of situation here, when the MU factor is less than 1, then potentially the amplifier will have some issue. They will be unstable. They have this potential to be unstable. So in this case here, okay, the amplifier may oscillate under certain load or source impedance condition. Okay, so beside the K factor, okay, we have this MU factor to determine whether the amplifier or the transistor that we actually design, they will be remain stable or not. Okay, so let's study the 5 situation. Okay, so basically under this case here, when K is less than 1 and this MU factor is less than 1, then this is so-called the potentially unstable, which means that they will be more highly so-called unstable design. Okay, so the circuit may exhibit oscillation or instability due to insufficient stability margin at both input and output. In short, the amplifier that we actually design, they will be potentially so-called unstable. So hence, because the so-called the margin, okay, basically they are too near, okay, at both the input and output. Okay, so basically this is what we call undesired. An amplifier with K okay, less than 1, and this mu factor less than 1, okay, the circuit may oscillate or even fail to function properly under certain conditions. So basically, this is a condition that we want to avoid, okay, because the amplifier that we actually design or the transistor that we actually design, they will be highly likely to be unstable. So another situation here, when K is still less than 1, but this mu factor is more than 1, then this is another so-called situation. Then the output will be potentially unstable, which means that only the output will be potentially unstable. For this case here, both the input and output, they are so-called potentially unstable. Okay, but for this case here, the output will be potentially unstable while the input is actually stable, in short. Okay, so basically, while the input is stable, the output may be unstable. Okay, this led to potential oscillation or performance issue here. Okay, so a filter with a stable input but unstable output, this actually led to unpredictable performance. So basically, this is at the input here, they are actually stable. However, at the output, they will be unstable. So with this kind of situation, okay, you may have some unpredictable performance. Let's take a look on another case here when K is more than 1, okay, which means that this is actually so-called acceptable now. However, this mu factor is less than 1. So this is what we call the input potentially unstable, which means that the input high chance, okay, it will not be stable, while the output, they are actually stable. Okay, so basically this is what you mean. The output is stable, but the input may be unstable. Okay, so therefore this may affect the overall circuit behavior. Okay, so an oscillator with a stable output, but an input that is actually sensitive to the impedance mismatch, this may become another issue. So basically, in short, you can see that basically this is both input and output, they are actually unstable. This is when the output become unstable. This is when the input become unstable. So basically under these three cases here, let's take a look on the so-called stable situation. Okay, so this is actually what we call the marginally stable. Okay, which means that although it's not that ideal, okay, but we can still do with this. Okay, but we need to keep this in mind. This is so-called the marginally stable, which means that we don't have a clear buffer and our design can be unstable. Okay, so under certain condition here. So therefore, under this kind of consideration, when K equals to 1 and this mu factor is equals to 1, we call this marginally stable. Okay, the circuit is on the edge of the stability at both the input and output, which means that they are actually at the edge, which means that any deviation, okay, this may cause the amplifier or transistor to be unstable. Okay, so basically, I will not say that this is so-called undesired, but this is something definitely we want to avoid. Okay, because most of the circuit we have some so-called variance, and if the variance actually fall on the wrong side, then we may not have a stability circuit. Okay, so a circuit that operates stable under specific condition, but they are actually very sensitive to the variation in parameters. So basically, this is what I mentioned earlier on. So basically, this is desire, which means that unconditioned stable, which means that 100% they will be stable. So when K is more than 1 and this mu factor is more than 1, this is what we call the unconditioned stable, which means that the amplifier design or the transistor that we actually design, they will be always stable. The circuit is stable, okay, under all linear operating condition, okay, at both the input and also the output. A robust amplifier design that actually maintains stability across a wide range of operating conditions. Okay, so basically this is what we want to be so-called desire. Okay, the amplifier design or the transistor design, they will be always stable. So basically this is what the 5 condition. Okay, the first 3, okay, basically potentially unstable. Okay, this is for both the input and output. This is the output will be unstable. This is for the input that will be unstable. Okay, as for the stable network, okay, so basically this is what we call the margin, okay, because they are just nice equals to 1, and this can be very risky. Okay, so this is a condition that we want to obtain, okay, which means that unconditioned it will be remain stable. Okay, we can actually stop the oscillation. Next, okay, so again, before I continue, guys, if you have really learned something from this video, please consider, okay, to like this video. For those, again, learn something, and if you are new from this channel, okay, please help to subscribe to this channel and also turn on your notification bell. Once again, thank you so much for strong support. Okay, let's quickly understand, Okay, what is actually a K? Okay, so basically this Rollett stability factor is actually derived from the basic stability condition that both the input and also the output reflected power, they must be always less than the incident power. In short, over here, you just imagine that this is what we call the incident power. Okay, we need to ensure that the incident power is less than the reflected power so as to ensure stability. So this is what you mean here. The ratio of the reflected power to the incident power at the input and also the output, okay, they are respectively called the input reflection coefficient and also the output reflection coefficient, as you can see from the equation over here. Okay, so first thing that we need to ensure so-called stability, okay, we need to ensure that the reflected power, they must be always less than the incident power. Okay, makes sense, right? Because once you have this so-called reflected power more than incident power, which means that so-called the load or the source, okay, we may have some active circuit. So this actually may be so-called challenging in order to design it back to so-called stable. So basically, this is what I mean here. The ratio of the reflected power to the incident power at the input and output, they are respectively called the input reflection coefficient and also the output reflection coefficient, which I have illustrated just now. So if a transistor, okay, basically when they are actually potentially unstable, okay, when K is less than 1, okay, so hence it is always very useful to know which area of the Smith chart actually represent the unstable region. Okay, so this region should be avoided when we actually design the matching network. Okay, so basically once we find out the unstable region, then we need to avoid this region when we actually design the matching network. Okay, so if not, okay, if you fall under this unstable region, the circuit that you actually design, they may oscillate. Okay, so again, this can be undesired. Okay, so in order to determine the so-called the reflection coefficient at the source and also the reflection coefficient at the load, okay, so basically they actually correspond to a stable design. Okay, for both the input stability circle and also the output stability circle. Okay, so we need to plot this circle. Okay, so later on I will show it to you how can we actually determine okay which region will be stable, which region will be so-called unstable. Okay, alternative. Okay, so if you have this instability, okay, that is actually always happen, then you can actually select a different biasing point for the transistor amplifier. Okay, remember that okay, different bias point, you actually will have different S parameters. When you actually have different S parameters, then your Rollett stability factor may be different. Okay, so basically this is what I mean here. So after that, you can in fact re-evaluate the stability or in fact choose a complete different transistor so as to ensure the design will be so-called stable. Okay, so let's take a look. Okay, how can we actually determine whether the circuit is stable or so-called unstable here? Okay, so if both S11 and S22 are less than 1, okay, so basically if these all are all less than 1, which is almost all the time, okay, always the case, then the center of the Smith chart, they will be always the stable region, which means that right at the center point of the Smith chart, this point is always stable. For this case here, you can see that this is actually the input stability circle here. Okay, so basically I mentioned here this part will be always stable. So all this part will be always stable, but over this part, basically they will be unstable. Okay, so this is the region that we want to avoid. So all these part they are actually so-called stable. Let's take a look on this output stability circle. Again, you can see that right at the center of the Smith chart, this part here will be stable. So therefore, it will be quite easy, okay, to conclude that this part will be unstable. The rest of this part will be stable. Okay, so basically this is how we can look at the Smith chart to determine okay, which region is actually stable, which region is so-called unstable. Okay, so more example here. Okay, so I always like to reiterate this here. The center point of the Smith chart will be always stable. So from here you can see that every point will be stable. So therefore, this is what we call the unconditioned stable, which means that I don't need to do anything. Okay, the amplifier design or the transistor design, they will be always stable as long as I ensure the load and also the source impedance will be so-called passive. Then I can actually ensure that this will be unconditioned stable. Okay, so let's take a look on these two cases here, okay, which means that I need to have additional rules so as to ensure that the amplifier actually work in a stable region here. Okay, so basically the first case here is basically the stability circle they does not cut into the center of the Smith chart, which means that, okay, so this point here is always stable, which means over this part here, this will be unstable. The rest of this part here, they will be all stable. Okay, so basically this is actually the stability circle, same as what I have illustrated earlier on. So basically this one, you can see that they actually cut over here. This part here will be stable. So basically I know that this part will be stable and this portion here will be unstable. So another situation here is when the stability circle actually cover the whole of the center of the Smith chart. This is actually the center of Smith chart. They actually cut, okay, inside the center point of the Smith chart. So again, when you take a look over here, as I mentioned earlier on, the center point of the Smith chart is always stable. So this part here will be always stable, and the rest of the zone will be unstable. Okay, so basically, I hope I have give you some idea how we actually can do some form of stability analysis in RF. Okay, so looking at the block diagram above, okay, so we know that the maximum power can only be developed, okay, when under this kind of situation here. Okay, for example, we have this transistor over here. Okay, so as to ensure the maximum power will be developed across the transistor, okay, firstly, we need to ensure that they are actually conjugate match at both the input and also the output port. Okay, so as to ensure the maximum power. Okay, so under this condition here, the transistor is said to be simultaneously conjugate matched at both the input and also the output port. Under this condition, the maximum gain you can get from this transistor network is called the MAG, the maximum available gain, which means that if you still remember, okay, under this so-called amplifier design, you have various so-called name for the gain. Okay, but for this situation here, this is what we call the maximum possible available gain. Okay, because if you still remember, okay, there may be some issue when the design so-called will be unstable. So basically, this is what we call the maximum available gain. Okay, so let's quickly understand the three different form of gain first. First one will be the transduction gain. Okay, so this is actually the actual gain of an amplifier stage, which include the effect of input and also the output matching network. And basically is governed by this equation here. So in short, basically this is the actual gain for the amplifier, okay, which means that we actually take the effect of the input and output matching network. Next will be the maximum available gain. Okay, so basically this is actually the maximum available gain, okay, that you can actually hope so as to ensure the transistor, okay, will be under this conjugate match condition here. Okay, so basically from here you can see that when K is more than 1, which means that this amplifier design or transistor design, they will be always stable. Okay, so basically we can compute what will be the maximum available gain, okay, from this equation here. Okay, before I come into this equation, I like to highlight this B1 term here. Okay, so in order to determine this MAG, okay, we need to determine the coefficient B1 first. So once we determine the value of B1, okay, if let's say the B1 is negative, then we need to use the plus sign in the MAG equation, which means that I need to use this as a plus. And if B1 is actually positive, then I need to use the minus here. So basically, in short, before you actually can calculate the maximum available gain, okay, so you need to calculate this coefficient B1 first. So once you calculate a B1, it can be either negative or positive. If it's 0, then you actually call this as positive. So once it's positive, okay, basically we use this minus term here. So if B1 is negative, then we will use the plus sign here. So basically this is how we can compute the maximum available gain. Okay, so next, okay, we also have this maximum stable gain. Okay, so basically this is when the transistor there is so-called potentially unstable, okay, which means that K less than 1. Then this MSG, okay, basically is defined, okay, as the maximum gain that is achievable while remain stable. Okay, so basically this is ensure that the transistor, okay, this is the maximum gain, okay, so as to ensure that the transistor that we actually design or the amplifier that we actually design, they will be always stable. Okay, so let's take a look on this equation or this graph here. So basically you can see that this is maximum, okay, stable gain. This is what we call the maximum available gain. So what's the key difference between these two here? Okay, so basically we note that the transistor is unconditionally stable. Okay, so basically onward 800 megahertz onward, okay, basically they will be so-called the transistor that we actually design, they will be always stable, unconditionally stable. However, below this 800 megahertz here, okay, the maximum stable gain is actually defined. Okay, so basically for MSG, okay, as it illustrated here, so basically under this situation, we have this potentially unstable, which means that this is actually potentially unstable. And this is basically the maximum stable gain that we actually can achieve. But at this so-called maximum available gain here, okay, so basically this is actually used for always stable so-called consideration. When K is more than 1, then we will be so-called calculate the maximum available gain. But if we calculate that the K is less than 1, then this is the maximum possible gain that you can actually achieve. Okay, so with this, I'd like to end my discussion. Please help to like, okay, and also subscribe to this channel. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.